Hello world and welcome back to Money Makes Games. In this third video in the 3D IK Spider series, we are going to be teaching our spider how to actually pick up its feet and walk. If you're ready, then follow me. My name is Money and I make games. Let's have a look to see what we need to get our walk cycle going. Now, in most animals and people, there's an ideal position for your feet to be so that you can maintain your balance and be stable. When you move or when you walk, basically what you're doing is that you are moving forward like this, but your feet, which are the green dots in this case, stay behind you. And then as soon as you start falling forward, you move your foot to the new ideal position and land on that so you do not fall. So this is what we would need to do to get our walk cycle for our spider going. First, the foot stays in place, we move the spider, and then when we've reached a certain distance between where the foot is and where our ideal position is, it's time to make a decision and move the foot forward to its ideal position. At any time during this lesson, if you feel that I seriously need some art lessons, feel free to hit that like and subscribe and help me to afford those lessons. To get the walk cycle working properly, it's not just enough to shuffle our foot. What we would need is to figure out where we are, where we want to be, and what the middle point is going to be, where we want our foot to go at its high point. Because we don't drag our feet, we pick them up and we put them down. So we'll find a point in the middle between our current foot position and our ideal foot position or our destination. And then from that middle point, we'll figure out a point perpendicular to our plane of where we want our foot to be in the air. So in other words, if we want to lift our foot up 30 centimeters, that point will be 30 centimeters perpendicular to this plane. Or if we're walking uphill like this, perpendicular 30 centimeters in between the 2 points. And then we'll take our step by moving our foot up to the high point and moving it back down to our destination. Want to know how we do this in practice? Let's go have a look. Now, before we can implement our walk cycle, we need to fix a small rigging mistake that I made. If you look at our rigging right now, you can see here's our foot target and it's moving the foot as expected. Now, when I move the body parent, which is how I'm going to move my skeleton, this foot should be following the position of the foot target, but it's not, because now my foot target is back here. The reason for this is that because my foot target is actually under my rig builder, we need the foot targets to be independent from the rig builder. So, to fix this, we are going to take the animator, which is essential for the rig builder, and we'll say copy component, and we'll just paste it there as a new component. And we'll do the same with our rig builder. like that. And then we'll go to the original sand spider parent and just remove everything. That's because we don't want our IK targets to move with our rig. So let's see if that fixed it. So here's our IK target. And let's move our spider body. And now the foot keeps trying to reach the target, which is what we want, because we want the body to move independently of the foot targets. Now, as I explained before, we need foot targets, or we need placement targets, to determine what the ideal position for our foot is in relation to the body. You'll see that under spider body parent, I created a new empty game object called placement targets, and I basically just added copies of all the foot targets to this. Now the difference between this and the IK targets is that this will always stay in the same place in relation to the body, because it's a child of this and it will move with it. Now if we look at this, I'm going to move the spider body forward, and you'll see that my placement targets stay in the same place relative to the body, while the foot targets stay behind. So now there's going to be a difference between the location of the foot position and the ideal body placement, which is exactly what we want to do. After that, we need to attach a script to our foot, which I've already created, to tell the foot when to move and how to move to reach that ideal position. So let's go to our script and see what's going on there. Now in my script, you'll see that I've added some fields. Firstly, there's my placement target. This is basically that ideal body position relative to the body. Then we've got the body transform, which I'll use to keep track of my body's position and its orientation. Then we have the step size. Now the step size is the distance between that ideal foot placement and the current foot placement that we are willing to tolerate before we have to pick up our foot and move it to the ideal position again. Foot speed is going to be how fast the foot moves from the current placement position to that ideal position. And the lift height is how high we want to lift our foot when moving it. Now I've added the minimum distance tolerance so that if our foot gets close enough to the intended position, it's considered to be there. You've made it, you're there. The reason why we're not bothered with placing the foot exactly is because it might be off by 0.006 or 0.005, which happens. And if that happens, the foot's never going to change its state and keep trying to reach that target, which might not be possible and which is going to cause your walk cycle to get stuck. Then we've got the opposing foot, which is basically a foot script. And in here, we're going to put the foot that's opposite to the one we have. Like with your 2 feet, you'll have your left foot as your opposite of your right foot. We'll be using this to monitor whether or not the opposing foot is on the ground, because it's impossible to walk with all your feet in the air. Right here, we have target position, which I've set to 0. This is where we want our foot to be heading at all points in the walk cycle. And then here we have step phases, which is an enum that I've created to help track our step phases. And I have a public enum, step phases, which is used to track the current step phase that we are in. And then I have a Unity event that's basically just telling everybody when the planted state of the foot has changed, which you'll understand later on. To start off, we'll grab our target position and set that equal to our placement target position. Why do we do this? Because initially we want our foot to start moving towards the placement target. That just gets everything going, and then when the foot reaches that placement target position, it's going to change its state. What we'll do in each frame is on update, we'll check firstly if the distance between our target position, our ideal placement position, and our foot's current position is greater than the step size. That means that our foot is planted further from its ideal position than we want it. And if our current step phase is resting, then we need to start moving our foot. Now you can see there's another condition here which says, and the opposing foot dot current step phase equals resting. In other words, if the opposing foot is not on the ground, we can't move this foot. Now that we've satisfied that we're supposed to be moving this foot, we'll set our target position equal to our lift position, which we'll determine down here in get lift position. Our current step phase is going to be changing to moving to lift. In other words, we are now lifting our foot and moving it to our knee-high position. And we're going to notify whoever's listening that we have changed this and the foot is starting to move. If we are close to that knee-high position, within the tolerance distance, and the current phase is actually moving to lift, so we know that we are moving to the knee-high position, and it's not just a coincidence that it's close to that position, then we'll set our target position to the placement target position. That's that ideal position where we finally want our foot to be at the end of our step. And we'll set the current step phase to moving to target. If we are in the moving to target step phase, we'll check, and when we are close enough to our target position, which is now set to that final foot placement position, then we'll change our current step phase to resting, which means we've placed our foot where we wanted and we're resting. And we've said on planted changed equals true. So in other words, we're letting everybody know that our foot is planted again and it's resting. After that, on every frame, we'll call move. In move, we check if our current step phase is anything other than resting, then we move. We'll take a vector 3, move towards our current position, which is transform position. We're moving to the target position, which we've set here and here, depending on the phase. And how far we'll move for each frame is determined by foot speed times time.delta time. The final piece of this puzzle is getting the lift position. Now let's have a quick look at our lift point code here. let's say our spider is currently at position, or at least our spider's foot is at position 1, 1. And we want it to be over here, going up a slight incline at position 4, 2. So that means the foot needs to move 3 units to the right and 1 unit up. That would be our placement position, where we want our foot to be, our ideal position, minus our transform dot position. So in other words, that's this minus this, which gives you an answer of 3, 1. And we want to know how to get halfway there. So we divide that by 2, as you can see here. And that means that we need to move 1.5 units to the right and 0.5 units up. Now that we know how far we need to go to get from there to there, we can take this position and just add the vector that we've calculated. So now we move 1.5 to the right and 0.5 up, and there we have our midpoint. Now, we don't want to shuffle our foot from here to here and then here. We want to pick up our foot by the height that we've specified in lift height over there. So what we'll be doing is we take our midpoint, which is here, and then we add the lift height to it. But of course we need a vector for direction. So we take the body transforms up, which is 1 times the up direction of the body transform, and we multiply that by the lift height. Now, in this case, the body transform might be something like, or the body transforms up might be something like minus 0.1 and up 0.9. In other words, to get from this position to that one, you need to go back slightly and up by almost 1. If it was standing on a level plane, this would have been 0, 1, which is also the normal transform.up. So why don't we just use transform.up? Well, this is okay if we're on a slight incline or a decline, but what if our spider was walking up a steep cliff or maybe even a wall? If you use transform.up, all of a sudden, instead of having a step that goes like this, you would have a step that moves like this, or even worse, something like that. And that's exactly why we have to get the body transform. And then finally, we return the lift point, and now we know where our foot needs to be heading. So let's have a look at the editor and see how that's actually implemented and how it works. Now that we're in our editor, we have our foot placement target set up. As you can see here, corresponding to our ideal positions relative to the body. And if we move this, the placement targets will move with the body. Whereas if we move the body, the IK targets should be staying put. So let's move the body again. As you can see, the iCase targets stay behind. Let's go to play mode. Moving the body. Targets stay behind and the feet follow the targets. So we know that's correctly set up. Then we find our feet. I've already added the script, but you will need to do this. So you add your foot script to each foot. And then to set it up, we'll be setting up our foot placement target for each foot. So foot 1 will be placement target 1. Grab it, pull it in there. The body transform, we can set up for all of them. So you can highlight all and drag the spider body parent in there. You can also, when you're setting these up, set your step size, set your foot speed, your lift height, and your minimum distance tolerance. You'll see I've got them on 13, 1.5, and 0.1 with a step size of 1. And then for each individual one, you need to set up the opposing foot. Now you can play with this as you want to. I basically went from the outside in. So the foot target for 1 has an opposing foot of left foot 4. So that's a pattern across like this. So this, and this. You decide what you want your walk to look like and play with this. Well, why did we do this? Why do we need to check the opposing foot? Well, it's basically just so that all the feet don't go up into the air all at once. And it gives a little bit of variance to how the spider walks. In other words, it just doesn't pick up all the feet on one side at one time and all the feet on the other side at one time, because that just doesn't look natural. So now that we've got it implemented, let's run it and see if it works. And there we go. That's our spider walking. In the next video, we're going to be doing some casting to ensure that each foot lands on the ground, so that if we walk over uneven terrain, our foot actually gets placed on the terrain. And we'll also do some fine tuning to this walk model. Until then, I am Moni and I make games.